Hi everyone, this is a video presentation of our student research project under the grant of NYU Shanghai 2017 Dean's Undergraduate Research Fund. I'm Qi Huang, a rising junior at NYU Shanghai majoring in data science. My team members are Yu Gai and Zhang Hao Chen. Both are rising juniors at NYU Shanghai majoring in computer science. It is my pleasure to present our thoughts and attempts of integrating memory mechanism into feed-forward neural networks here and hope you will enjoy the video. First and foremost, let me briefly introduce our project. We formulate our research goal as to integrate attentional memory to feed-forward neural networks, and during the research, we explored various ways of integration, of which the details will be shown later in this video. Despite these attempts, we also advanced our understanding of recent progress in CNN architecture design from a memory mechanism perspective, which is kind of new. Okay, so let's start from our motivations and project significance. Before the start of this research project, we noticed a sort of interesting fact. Although the idea of memory in the paradigm of RNN is pretty common now, the idea of memory in CNN is relatively underplayed. Barely any attempt was made in adding memory to feed-forward neural networks now. Nonetheless, it seems like this is a promising direction for us to try, even in an intuitive sense. Essentially, memory serves as a quick and efficient gateway for higher layers in the pipeline to have access to lower-level representation. Then the question is why lower-level representation are important anyway? That's because for many of the times, they contain some basic features like lines, curves, and contours of the objects, and these features will be very useful in some tasks. For instance, when feed-forward neural networks are employed to do tasks like semantic segmentations or object masking, it will be very useful if the output layer can have direct access to low-level features stored in low-level abstractions and then utilize them directly. We think that would be better for the high-level layers rather than let them to try to rediscover those low-level patterns from the already high-level representation they inherited directly from the upstream layers. Therefore, we deem it meaningful to explore potential ways of adding memory mechanism to feed-forward neural networks. During our research, we found that actually some recent progress made in neural network design can be regarded as the most primitive form of memory mechanism. Residual neural network proposed by Kai-Min He et al. In 2015 introduces identity connection, aka skip connection, to CNN architecture, and they enable downstream layers to have direct access to information processed several layers before it through the short path. This kind of design sort of creates a series of chained but most of the time locally connected memory mechanisms. Another paper proposes densely connected convolutional neural networks, also known as DenseNet, and their design concatenate all the feature maps of previous conv layers to the next conv layer. This can be thought as indiscriminately congregating all the previous feature maps for higher level layers to use in later. However, drawbacks exist in ResNet and DenseNet. Essentially, they utilize different slots of memory indiscriminately rather than selectively. DenseNet, for example, let feature maps of all previous layers be passed down with equal weights, though sometimes some feature maps in a certain layer can be reasonably more important than the others. Therefore, we think we may need some better way to improve the memory system. Furthermore, memory capacity is somehow limited. Therefore, network must focus its memory space on preserving crucial information rather than all the information. Therefore, we think one of the ways to improve the memory system or to integrate a better memory system into the conventional architecture is to invent or define an attention system to manage our memory.
Then I will present you with a summary of our experiment results. Our exploration of integrating memory mechanism to traditional feed-forward neural networks starts with simple deterministic memory mechanisms. Our first trial is constant attention network. Here, we are making the assumption that all intermediate representations should have equal importance and thus be treated equally. The formulation is that the memory at step t is equals to the summation of memory at step t minus 1 plus current representation, followed by a batch normalization process. The batch normalization is introduced here to avoid the problem of grade vanishing and help optimize deep neural networks better. However, the assumption here is sort of problematic, as obviously not all intermediate representations have the same importance. To address the problem with the assumption of the constant attention network, we put forward the decayed attention network with the assumption modified that the importance of the intermediate representations decays with time. The assumption is based on the observation of the timeliness of most data events, more or less. The formulation is therefore that the memory at step t is equal to decay rate times the memory at step t minus 1 plus the learning rate times current representation. Note that here a smaller decay rate represents a higher decaying rate of the memory. The experiment result is shown in the graph. We experimented with different decaying rate settings, represented with curves of different colors. The blue line, which represents the setting that does not decay the attention, with time performed the worst with a validation accuracy of about 87% after about 80 training approaches. For the other settings, we observed that the red line with a setting of decaying rate 1.0 achieved the best result with a validation accuracy of about 92%. However, there are cases that an earlier intermediate representation has a higher importance than recent representations when those earlier intermediate representation depicts crucial characteristics of the input needed by certain tasks. Therefore, we have the idea that a measure of the importance of previous intermediate representations should be adopted to determine the extent to which the intermediate representations should be utilized. Our formulation is as follows. The memory is equal to a stack of intermediate representations, and we have a score which is a convolution network with its input being the current representations. And we input the score to a softmax function to compute a probability weight matrix. And we have the utilized memory map computed by multiplying the probability matrix with the previous memories. Here we are showing the crucial codes of our attended memory network. The attention network function is made of a normalized convolution layer followed by a global average pooling layer and a fully connected layer, outputting a score which is then being used to compute the probability matrix with a softmax function applied. The re function then element-wisely multiplies the probability weight matrix, which represents how much information in the corresponding memory slot should be utilized, with the memory matrix to output the memory that is going to be utilized. Our previous model is still sort of primitive, inspired by the massive adoption of LSTM long short-term memory networks, a variant of the vanilla recurrent neural network structure. To address the attention problem in the field of natural language processing, we transferred LSTM here as a control head for memory, so that it can be trained to evaluate the importance of intermediate representations and selectively utilize them. As a recurrent model itself, LSTM can recurrently refine its evaluation results so as to achieve better performance. Here we are showing the crucial codes of our model. The LSTM function implements the long-short memory structure for controlling memory. The read function implements the memory reading control. It simply applies a convolution transformation on the hidden state output by the LSTM. The write function implements the memory writing control by applying LSTM on the current representation. The LSTM will then determine how much previous representations should be saved and how much the current representation should be written to the memory, with length parameters. The experiment result is shown in the graph here. The validation accuracy graph is on the left, while the training accuracy graph is on the right, with the baseline being triple-state residual network. Here we can observe on the right graph that during training, our model achieved a better result than the baseline, while during validation, they achieve approximately the same results, which may imply a generalization problem to our model. Also, we noted that our model achieved a competitive result at the cost of huge size of parameters and states. Compared to our baseline, which has a parameter size of 0.3 million and 1,000 states, our model achieved the result at a cost of a parameter size of approximately 0.7 million, more than twice of that of the baseline, and a number of states of 14,000, nearly 14 times than the baseline.
Okay, so here comes our conclusion part. As we said previously, we are motivated by the observation that there lacks memory mechanism in conventional feed-forward neural networks, and we try out a variety of methods to add memory modules to state-of-the-art CNN architectures. We start from simple deterministic memory mechanisms and gradually move on to more complex mechanisms involving auxiliary network for evaluating importance of memory slot. Nonetheless, the performance improvement we realized in our experiment does not seem significant enough, and therefore future work is definitely needed. Regarding future work, firstly, we can try and integrate more complicated RNN as the auxiliary memory network. Grave et al. At DeepMind proposed a neural network system with dynamic external memory in 2016. Also, there is another paper known as Memory Augmented Neural Network with Wormhole Connection by Goucher that can also serve as a reference for us. Secondly, we may need to find a better benchmark for future experiments. During our research, we tested our thought primarily on MNIST and CIFAR10 dataset. And these two datasets have actually relatively small capacity, and they may not need the assistance of low-level feature to handle. Promising candidates of dataset for future experiment include human post-estimation dataset and semantic segmentation or image masking dataset like MS-COCO or VOC. Thirdly, if we try to rethink our understanding of the role of memory mechanism in neural network, we may focus too much on how to build a memory, but forget about a more fundamental, although a little bit subtle question: how memory can be used if there's any. In fact, we cannot expect the current layer design can magically learn how to use the memory we generated. That's because these layers are not simply designed or created for such a use. A paper from UC Berkeley called Human Post-Estimation with Iterative Error Feedback actually provides us with an argument that conventional convolutional feed-forward architecture can learn dependency in the input space, but they lack the capacity to learn dependencies in the output space. This sort of thing is very useful for us. Therefore, in the future, we will think about how to add modules to the existing pipeline to handle the memory we generated, rather than simply throwing them to the existing layers. These are all important thoughts, and we hope to further explore them in the future. That's all. Thank you for your attention, and have a nice day.